So, okay. Again, good evening, everyone, to the Your Personal Trainer Series Episode 2. Alessandro, you are there?
Yes.
Okay.
Hello, and welcome to everybody. So, let's start with some housekeeping. Some information about the platform. You can use the controls to ask questions, so feel free to ask. We will answer during and after the webinar. We suggest you to put the GoToWebinar in full screen mode. And also we will launch a final survey, so we will kindly ask you to respond. Your Personal Trainer series. We are at second episode. This is a series that has been thought for our customers, in which we will, in each episode, we will give you some very, very valuable tips and tricks to use our products at full potential. We started in June with SOLIDWORKS Simulation episode, and today we'll be focused on SOLIDWORKS Flow Simulation. If you followed the first episode, you will you maybe remember that it was supposed to be in July, and so but we delayed it. There is a good reason for that, because Alessandro has become father. So my congratulations to him.
Thank you, Alessandro.
Okay. Next episode will be in early November. It will be called Your R&D in SOLIDWORKS. Actually, it is being conceived from a presentation that we gave at SOLIDWORKS World 2015, and we will show you how you can use some advanced tools to do R&D with SOLIDWORKS. In November, we will show you some design to manufacturing workflows. And finally, in December, mechatronics design integrating mechanical, electrical, and PCB design. So, something about the presenters. My name is Alessandro Tornincasa. I'm an Euromed Territory Technical Manager, and with me today there's Alessandro Bellini, Senior TTM and also Simulation Specialist.
Good evening again.
And thank you, Alessandro. And we decided to call our team a simulation team, because our aim is helping customers innovate their products with simulation, and we work in a territory that includes Italy, Turkey, and most of the Balkan countries. So today we'll first give you some insight about the value of virtual prototyping with simulation. Then we will explain you what are the key technologies in SOLIDWORKS Flow Simulation. Alessandro will show you some valuable documentation that proves flow simulation solver reliability. Then we will show you some tips and tricks on free surfaces, rotating region, and also how to manage transient results. And finally, I will explain you how to submit ideas to guide the development of flow simulation. Okay, let's start from the value of virtual prototyping. This is the traditional approach, the traditional product development cycle. So you start with a concept, then you engineer it, and finally you validate with some prototypes or with some simulations that are performed by an expert or maybe by a consultant. This approach is okay as long as you don't have issues. If you have an issue, you cannot change the concept, because you don't have time. You are in a phase in which the design has to be delivered. So you need to modify what you have, and very, very often it's very expensive, and you don't have much freedom to edit your design as when you are in a concept phase. So there are some limitations in this approach. So it's obviously very problematic to edit an existing engineered design, and it takes time to edit the design. And also creating prototypes or doing analysis at the end of the cycle is very, very complex because you're working on a model that has not been conceived for simulation. And also there are few resources because you don't get many consultants in the market or experts on finite element analysis. And you don't have actually the time to find an optimal solution, or you are editing something that is existing while the optimal will be editing the concept. And therefore there's no time to explore alternatives. It's like you're going from point A to point B, where point B is your optimal design. You might lose your ideal path to the optimal design, like navigating with a paper chart. And if you lose track, it takes a lot of time to get back on track. So not using simulation is like navigating with a paper map. This is the product design cycle that is guided by simulation. It means that simulation is performed right after the concept phase. So if you find an issue, you can immediately fix it because you fix your concept. And this is very, very easy because it's a model that is simplified. Simulations are very, very quick, and you can quickly validate your ideas. And the system even has some tools to automate ideas validation, like parametric studies that compare ideas and find the optimal design. So the value of simulation-driven design is obviously time and cost, because you are compacting the development cycle. You improve quality because you are conceiving an idea that is optimal from the start. You don't have to cycle through many ideas. And also, it's much quicker to edit a concept than editing an engineered product. So you get your product quicker to market. And also this way you are innovating because you have time to validate many ideas. So it's like you're navigating from point A to point B with a GPS. If you lose track, the GPS will immediately put you back on the right track. So next, technology in SOLIDWORKS Flow Simulation. There are 7 key technologies in flow simulation. The first one is that you're working in the SOLIDWORKS interface, so you don't have to transfer data to another tool. And also, flow simulation is as easy as using SOLIDWORKS. You learn it very, very quickly. It's associative, so if you change your CAD model, the geometry you're analyzing will update accordingly. The mathematical models are proven. Alessandro will show it to you shortly. And the meshing is automatic. The fluid region is generated automatic. Also, the meshing is very, very easy to manage. And there are some very powerful tools that allow you to do what-if studies and automatic optimization based on a design goal. The solve is very, very easy to manage because there is an automatic convergence control. So the calculation will stop automatically based on a very, very simple criteria. And also the model to model laminar and tubular flow is automatic and very, very easy to set up. Some typical applications in internal flows, like calculating pressure drop in valves, or finding the flow coefficient for valves. There are even customers that are using flow simulation to simulate extrusion process. Or another interesting application is the fan curve determination by running a series of studies with different flow rates. Heat transfer is a very, very popular application. So you can calculate heat exchangers, solar heating, windscreen de-icing, really many applications. Also, you can calculate external flows like aerodynamic testing or even noise level. Also, there are applications in mixing, so you can find out what are the concentrations of 2 fluids that are mixing. And also force prediction, so you can calculate what's the force on a turbine and you can use also this information to calculate the drag on a moving object and the aerodynamic coefficient. Finally, Alessandro will show you shortly the application of the rotating mesh. So it's a more accurate approach that will actually make the mesh move and do a transient calculations and give you more precise results, and it will allow you to simulate models with non-axis symmetric flows, and also will allow you to create a very realistic animation because you see the object moving at different time steps. So the next step will be flow solver reliability. So I will pass the screen to Alessandro.
Okay. Okay. Alessandro, can you see my screen?
Yes.
Okay, perfect. So let's talk about the reliability in flow simulation. Basically, the concept is industry proven. So I would like to share with you, because sometimes it's a little bit hidden in the installation. You have, if you have flow simulation, you have already a lot of documents actually to prove that the real data, the test data, are really similar to what is calculated from flow simulation. This is the path in your PC to find out the documents. There are more than 28 examples with 2D and 3D models, so also the models are available, and the comparison to the experimental data. Some examples including convergent divergent channel, at sink convection, natural convection, porous media flow, impeller, of course, we will see something about rotating region, cavitation, thermoelectric cooling, and so on. Many examples. I'd like to now to show you the PDFs. So, for example, this is the validation example I am talking about. It's in your installation folder right now. For example, here you can see a duct, 90-degree band square duct with all the test data and all flow simulation data of the comparison, or you can see other example as well, also in 2D. So it's a very good start to understand not only that the solver is reliable, but also how to start with a specific case. Also, it's present the tutorial section, the tutorial document in flow simulation. And for example, you have just to start with the first examples, very basics, some advanced examples, like the CPU cooler that I will use also for presenting some tips and tricks. Okay. Also, it's very useful because you have all the information on how to set up this particular analysis. Also, the last document that I will show you is the technical reference. And apart from the nice image of Star Trek Enterprise, basically this document is about the numerical approach. So how the mesh is performed, how's the all the functions, all the approximation, all the equation that are used, and so on. Okay, so if you are really you want to dig into this kind of specific approach. So let's talk about an example. Here I have selected this flow over a cylinder. So you can see the flow with the low Reynolds number and the high Reynolds number. So a turbulent and laminar. And you can see this is from the example. So you can see the real results and the flow simulation results. Also, Alessandro will show you an animation of the von Karman street in some minutes. Also here you can see a comparison of flow simulation data with the real test. So very, very useful tools to start and to understand that the flow simulation solver is very reliable. Okay, so let's go to the main section that is about tips and tricks. We will show you a lot of things. I'm sorry, we will rush a little bit, but of course the webinar is being recorded, so you can review the recording how much as you want. So don't worry. Rotating region, it's very important. It's from let's say 2015, if I remember correctly, but I think it's worth to understand better how to use it. Also, free surface, it's new from last year, from 2018, and maybe some of the customers have skipped this. They don't know the existence of this feature, and it's very important. I would like to share with you some examples, some tips and tricks. Optimization. So Alessandro, then we talk about optimization strategies and some other information, and something about also post-processing. So also animation of the results is very important when you have to present something to your manager or to the customers and so on. So let's talk about the rotating region. Basically, in flow simulation, you have two ways to analyze a rotating device. One is averaging rotating region. That is, as the name implies, means that you are averaging the values. You are not really estimating the real, let's say, rotating impeller or device. And the other one is sliding. Sliding means rotating mesh. So the mesh is really rotating, so you can understand better what is going on. When to use? Basically, the rotating mesh technology, the sliding technology, is meant to analyze real geometry of a rotating device. So you want to design and to analyze your geometry, so the better is to use a sliding region, rotating region. And of course, you are interested in the time progression of the results. Of course, you are interested also in the behavior in the steady state, but in this case, also it's very important to understand how to progress to the steady state. So you are analyzing also the time frame. When not to use the sliding and to use the averaging, when you want just to analyze the overall behavior, you are not, let's say, interested really in each time step before a steady state. So you want just to see what is the steady state. Or, for example, you are dealing with purchased components. So fans, rotation impellers, turbines, and so on. So you don't deal basically with the real geometry. You just want to understand the effect on the other domain, on the rest of the domain. And of course, you are interested only in results at operating speed, at the steady state. So let's talk about the feature itself. When you are creating a rotating region, you need this kind of engulfing design. Let me write with the pen. So you can see here that I have, sorry for my skills on the pen, is not the best, but this is the rotating region. Has to be axial symmetric, and in this case it's also engulfing, it's overlapping these other components that are static. So, and that there is a reason that it's a suggestion to do that. Let me erase this one. Okay. So when you are creating the rotating region, the best is to be very, very simple, so not too much geometry, and it's the best to engulfing completely the rotating device. It's not the best, it's mandatory that you have to engulf completely the rotating device, and if you are near to a wall, to a static wall, the best approach is to overlap that wall. Also, because you are avoiding, like here, you are avoiding a thin gap. So the best is to avoid the gap and to overlap the wall. Also, another suggestion is to leave enough air in the axial direction to leave, let's say, the solver enough information for the intake. The overlapping, if you are creating a rotating region like this, you are overlapping some components, and in this case, you have to apply onto overlapping regions. You can also select just entirely the components that are fixed. You can add this kind of boundary condition that is called real wall, and you have to activate the stator condition. Okay, and it's much more preferable than avoiding with a small gap this kind of line. Better is to overlapping the region. Let's talk about the time step. Why time step? Because if you are using a rotating mesh, this implies automatically the time-dependent analysis. So you want to set up a time step. Or let's say you have to use a time step, but you can set up it in a better way. So the first way is to leave it automatically, but don't get me wrong, the software is doing a good thing, but sometimes it's too much. Let's say it's calculating a lot of data. So the risk is to wait a lot of time just to have maybe a rough analysis. So the suggestion here is to use a manual time step for a better control. So better control, I don't mean precision. With the automatic time step, you have precision, but maybe you are wasting a lot of time. With the manual time step, you have a better control and a compromise between precision and time spent on the simulation. So for a rotating device, I suggest to calculate the time step from 1/5 to 1/10 of a single blade movement. So let me explain with this example. I have here a rotating device with 500 RPMs. So it means 0.12 seconds per revolution. And I have 8 blades on this fan. So the time step here is 1/8 per 0.12 seconds per revolution per 1/10. So this means 0.0015 seconds, or even less if you want in this case. If you are in a situation that you want to, let's say, spend less time, you need just a rough analysis, you can short the time step, let's say, up to 1/5 or even 1/3 if you want. Okay. Also, it's very important to remove travels and goals convergence and activate the physical time. What I mean, in the calculation control options here in Flow, let me switch Flow. Okay. So here in Flow Simulation, you have to go to calculation control options. And here I have already shown you the time step have to be set to manual and input the time step. And in the first page, normally you will see like this. And it is not suggested with the time-dependent analysis because basically travels means that the calculation is stopped when the results are traveling 4 times the domain. And that is not that you want. I will explain in a bit. Also, goals convergence is not what you want to stop the analysis, because in this case, basically you want to stop the analysis only when you are at the end of the time frame that you have thought. So basically here 1 second. So this is the suggestion for this kind of analysis. Let's talk about now about free surface. Free surface is new from 2018. Maybe many customers haven't used it, so I would like to give you a good idea to approach this feature that is very, very interesting. So This is the overview of the physical model. Basically, it's based on volume of fluid approach, and the main focus here is on robustness and performance. There are some limitations, of course, so it's better to know. For example, the two fluids are to be immiscible. We cannot mix together two fluids. So we have here an example of pouring the tea in a cup. So basically, we are talking about a liquid and a gas, or two liquids, for example. Okay. The density cannot be much more than 10 at the power of 4. Mach number is limited. Of course, it's always transient because we are developing the flow. So we are interested in the transient analysis. And there are some limitations on the surface tension. We cannot have results. We cannot take into account surface tension. We cannot use the rotating mesh with free surface. And we cannot have phase transition. Some examples, some interesting examples that we can do, we can analyze with the free surface. We are talking about tank filling. Very, very nice approach. We can input and we can understand how much time is needed to fill a tank. Also, the sloshing in a tank. So we can apply forces, we can apply movement and inertia, and we can understand how much is sloshing the water, for example, in this case, and how much force is producing on the tank. Also, we can approach to fountain, so we can see what is the height of the fountain, we can see the spreading of the water, and so on. Also, another nice application is about wave making resistance. So in a boat, in a ship, we can see the wave process, the wave, also the resistance to that. How to use it? So first of all, to use a free surface, you have to activate the analysis type in the first window. Okay. And this is automatically forcing the time dependent and automatically is making unavailable some other choices like rotation, humidity, and so on. Also, you can set up initial conditions. To do that, the best is to use the dependency type, if of H. This is available only if you use gravity. So in this case, you can set up, for example, a level of water. So it's very nice because this is maybe the starting point of the simulation. Okay. Also, the same thing can be done inside the fluid subdomain. So if you want to analyze, if you want to use the free surface feature only in a portion of the domain, you can use the fluid subdomain here. You can define just a face of the subdomain. You have to input like here an immiscible mixture. So then you can add fluids like air and water together. And in substance concentration, you can again use the F of H table to define which is the initial level of the water of the air. Also, very nice feature is the ability to create a solid as an initial condition for the liquid in this case. So you can just in the example here on the left, you can design, you can just model this solid, and then you can define initial condition, boundary condition. You can select the solid. You have to disable it. It's normal. And you can assign it as a water, for example. And then the simulation will start with this as an initial condition, initial level of the water in that case. Very powerful feature. Also, as I mentioned, we can analyze ship and vessel wake resistance and wake generation. Again, here are some tips and tricks. It's better to add the solid if the bottom is present and it's not too much, of course, because also it has an effect of on the wake generation. You have to make the domain sufficiently large. What I mean here, for example, it's submarine, and you have to count the width of the submarine from 5 to 10 times on the sides, and also up and down. And for example, in the front, so upstream and downstream, you have you need at least one length of the object. Okay. Also, the model is capable of simulating waves. You can input, but at the moment there is no user interface. So you have to input the equation of a wave, and this can be used as an initial condition of rough water, for example. Okay. Also, in the meshing of the free surface, you can use the solution adaptive refinement, the mesh adaptive. So in this case, the mesh is recalculated each iteration in terms of in terms of results that we want to see. So in this case, it will follow the flux. So this stream of water that is pouring into the other recipient. So basically, it's very interesting because it's completely automatical, but of course it's time consuming. So some tips: don't use it for chaotic flows. Use only for let's say very well defined flows like here. Also, avoid to use more than 1 or 2 levels of mesh refinement. Okay. Okay, let's talk about results. Here is a very nice animation of a sloshing tank. In this case, the approach is based on the volume fraction. I will show you inside Flow Simulation. So let me start from here. Okay. Let's check, let's say another time moment, for example. Okay, let's say this. Okay, so you can see from this, let's say this plot, it's like having the fluid that is sloshing into the tank. How it's done? Basically, I will start from scratch. So, okay, you have the model. It's transparent, so it's just SOLIDWORKS. So you have to select it as transparent. Then you have to create a surface plot of the inside surfaces. So let's check the definition. So you can see here I've selected the inside surface of this tank, and then I've selected volume fraction of air. You can select also volume fraction of another liquid or gas. It depends on the simulation. In this case, air and water. You have to input just 2 levels of information. Why is that? Because in this case, you would see only if there is water or not. And from the legend, you can input the maximum as 0.5. So after this, it will just not plot. Okay. This is for surface, so you can see that it's missing something. So the surface is only on the inside of the tank, and there is no, let's say, closing surface of the liquid. To do that, we have to create an isosurface plot. So I will enter into the definition, again, of the volume fraction of water. And again, the same value, 0.5 as before. Also here, I suggest you to use a fixed color, like this in blue, for example, and a little bit transparent. We can, of course, adapt, and we can do it in this way. Okay. Okay. So like this, it seems okay. So in this case, now it seems to represent the volume of the liquid. Also in the Transient Explorer, we can see it better. And Alessandro later will explain more about the Transient Explorer. So in the Transient Explorer, I can see now, maybe it's slow through the connection, so I apologize for this, but of course you can review the registration, the recording, sorry, later. Okay. Also, I can use it manually, and it's a very nice lot of these sloshing liquids. Okay, so let's continue with the optimization with Alessandro Tonincasa. Alessandro, you're there?
Yes.
Okay, perfect.
Okay, I will show an interesting case. The aim is optimizing an heat exchanger. This is the input data of a heat exchanger. There's hot air, 350 Celsius. The flow rate is known. And also there's some cold water with known flow rate. And at the outlet, the aim is finding out the temperature of air and of water in order to find out how efficient was this heat exchanger. So I'm going to show you right now the model in SOLIDWORKS. Okay, so this is the heat exchanger. I can create a section view to show you the design. I have created a flow simulation study. As you see, there are some boundary conditions. The inlet mass flow of hot air at 350 Celsius, inlet mass flow of cold water, and then environment pressure at the outlets. And obviously, these are two fluids that are not coming in contact, so I had to define some fluid subdomains, one for air, and the other fluid subdomain was defined for the water. And then I put some goals on velocity and temperature, and also some equation goals to calculate the temperature reduction of air. So let me show now how the results. So I will quickly load them. Okay. I created a cut plot to better show you the temperature. I can obviously find out the outlet temperature of air using the flow simulation tools like the probing. So I can find out that the hot air now is getting out at 260 degrees, or I can simply use some goal plot. Then I can generate some flow trajectories and I can animate them. Okay, let's say that I'm not satisfied by this model. I want to explore some more design alternatives. So the beauty of SOLIDWORKS Flow Simulation is that you can explore as many design alternatives as you want, even if you're not an expert of heat exchangers, exactly like me. I'll show you the design ideas that I had by using the 3D views. You can display these 3D views with any SOLIDWORKS standard license. And if you want to create them, you can use SOLIDWORKS MBD. This is a very effective way of presenting something to customers or colleagues in design reviews. So this is the basic model. As you can see, the length is 500 millimeters. And this is a section view that highlights the internal regions of the heat exchanger. The first idea I had to improve this design was improving the design by modifying the pipes. So this is the basic configuration with the pipes. I created another configuration with some fins, big fins on the pipes. Another configurations with more pipes but no fins. And another configuration with the same number of pipes but smaller fins. And then the other designs are a much longer heat exchanger, 2050 millimeters, 2250 millimeters, and this is a section view. Actually, it is a broken view in 3D that shows that there is a low number of pipes with big fins. And then I created a slightly shorter version, only 2000 millimeters. And if we look at the inside with the broken view, we can see that there are more pipes with smaller fins. So how do you analyze all these configurations in flow simulation quickly? If you remember, I have already set up my flow simulation study for the default configuration, and here I have all the other configurations. What you can do in flow simulation, you can clone your study, and you can choose where you want to clone your study. I want to clone it to the other configurations. I also keep my results so that I can make some comparisons. So what flow simulation will do will copy the study and retain all the boundary conditions, the goals and the plots, so that when you're ready to go, you just need to run all your studies. As you can see, in a few seconds, I'm preparing some very, very complex setups, but it would have took me at least 5 minutes for each study. So you can see now I have more studies, one for each configuration, and I can even run them. I don't need even to run one by one the studies. I can use a tool that is called batch run. It means that from this screen, I can decide which studies I want to run, and I can also decide if I want to just mesh the study, if I want to solve it, if I want to use all the cores for that particular study or only a few cores. And if you want, you can use an interesting functionality that is called remote solver. It doesn't mean that you are distributing the calculation in many computers. It means that the simulation can be run on a computer with more power designed for simulation. So say, for instance, you have 10 people that are doing some R&D. They can have a computer that has been configured for SOLIDWORKS, and then they can launch the analysis on another computer that has been configured for simulation with more RAM and with a faster CPU. Also, as long as you're here, you can also prepare batch result processing. It means that for each study, I can decide the output that has to be saved in the study folder. So the flow simulation can save a picture of the cut plot for each study, also the goal plot, the Excel file, and if I want also, it can generate the report automatically. So this way, I have a quick tool that allows me to compare many design alternatives. Okay, I'll show you the designs. So as you can see, I think that the 3D views have been very clear. This is the short version with some fins, the long version with the same number of pipes and the fin geometry, the short version with more pipes and smaller fins, and the slightly shorter version with more pipes and small fins. I'll show you now the results of this heat exchanger. So let me close this one and show you the other design with already calculated results. So when you're here, you can use a tool that is called compare results. This tool, you can launch it from here, from the results, and it will allow you to select your studies and also what is the result that you're going to compare. So from this window, you need to select the studies, and then you need to select the results. And inside of the software, you'll see the results. This is the summary of the results. What I'm very interested is it is in this row, which is the air temperature. It's showing me the final temperature decrease of air for each of the studies. If you want, you can get some visual hints like highlighting the min and max value. I'm obviously interested in the max values. So in this case, I'm having the max on the longer version of my heat exchanger. You can also display them in tabular format, which is more intuitive. So I'm going to look at the last plot on the right. So from the bars, you can see the red one and the green one are the longer version of the heat exchanger that provide the biggest temperature reduction to air. And you can, of course, export all of this to Excel to elaborate the data better. I'll show you the plots that I will get from Excel. So this is the temperature decrease of air. Obviously, the biggest decrease is provided by the longest heat exchanger. More or less, the results are very, very similar between the 2000 millimeters and the 2250 millimeters heat exchanger. So it would be a good guess in this case to choose the shorter one because it has less mass. So in the plot on the right represents the mass of the configuration. So I would choose the 2000 millimeters heat exchanger that has less pipes and big fins. What I've shown you is not automatic, even if you've seen that it's very, very quick to set up something like this. It took me really a few times to create all these comparisons. You have some tools that can even automate further your research of the best design. We have a tool called parametric study that will allow you to set up some parameters, some dimensions of your model that can vary, and you can launch many studies in batch and see how your result, like temperature, is varying as the parameter dimension is varying. So when you change the geometry, how it's affecting your final result. And you get also goal optimization. In this case, you put a constraint, so you decide what dimensions you can vary. Then you put a goal, like maybe a max temperature decrease, and based on this, the software will figure out what is the best design that will respect your goal. So we'll do all the job for you, and you can optimize the design by varying more than one parameter. So I could vary the length, the number of fins, the number of pipes, the thickness of the pipe. You have the freedom to find the best design. We will speak more in depth about this in next episode called Your R&D with SOLIDWORKS Simulation and Flow Simulation. So for example, as you see in the picture, with a system like this, you could easily even create a pressure drop versus flow rate curve for a valve, because everything is automatic by SOLIDWORKS Flow Simulation. Okay, next will be how to manage transient results. You have two options. The first option is the Transient Explorer that Alessandro showed you a few minutes ago. This is used when you don't need to save a movie. You just need to explore your results at each time step. If you want to create an animation, you need to save the full results. And in this case, you can animate surface plots, cut plots, flow trajectories, ISO surface plot to see how the behavior of the system when time varies. And I think that Alessandro would like to show you an animation of the rotating region with this approach. So I will pass in the screen. Okay.
Okay, so let's share back my screen. Let me know when I'm back. That's right. Can you see my screen, Alessandro?
Yes, we can see it.
Okay, perfect. So let's say we have the transient results. So now we want to present better the results, maybe to my manager, to the customer, and so on. Okay, so I would like to have something like this animation of the flow trajectories, or an animation of the blades, or together, and so on. So let me switch to SOLIDWORks. Okay, now we came back to the fan analysis, to the CPU cooler analysis. We have the results and we want to animate them. So first of all, I have to hide what we are trying to animate from Flow. So in this case, I will hide this. I will hide this one. And then I have to create a surface plot here. On the surface, we can just select the component that you want. We don't need to select all the surface each one by one, and we can, for example, plot the temperature. So in this case, I can see the surface plot like this one. Okay, and this is very simple. We can see the temperature or just a color or whatever you want. Okay, it's configurable as you saw before. Now we want an animation of the blades, for example. So you have to insert the animation, very simple, and then you have to click to wizard. In the wizard, we can delete all the existing tracks. We don't need to rotate the model, and we have to use a scenario option. The scenario option will tell the software to input all the information from the time step. Okay, and of course you can use a uniform distribution or a proportion. Why is that? Because if you're using automatic time step, you need to reset up. Let's say you may end with a different span of time steps. But if you are approaching it as we suggested with the manual time step, of course you will have a uniform distribution. The units is a physical time from 0 to 1, and let's finish it. Okay. Now I want to use, for example, this surface plot. So in this case, in this animation pane, you have to go to surface plot here, right-click, insert control point, and slide to the final point here. So now let me try to animate the results. Maybe it will not be so fluid from the other end, but again, you have seen the PowerPoint, or you will see the recording itself. So from here, then you can just review the animation, and then you can save in AVI format or whatever you like. Okay, so very simple plots, very simple steps, and you will have something like this. So to summarize the steps, be sure of saving each time step. This is done in the saving of the calculation control options when you have activated the transient analysis. Remember to activate the full results saving for each period that you want. Maybe not all the iteration, or maybe for each iteration. Okay. Another one then is to use the wizard tool in the animation pane. So basically you have seen it in action. Then you have to select scenario in the wizard, and then you have to insert the plot that you want to animate, or the plots that you want to animate. You can have multiple plots then that you can animate together. Of course, you have to try for yourself. It's very, very nice to see what is like to do. And then you can save the movie. Okay, so at this point, I will pass again the slides to Alessandro for the remaining.
Okay, thank you, Alessandro.
Perfect.
Okay, I'll show you quickly another example of transient result that is applied to a thermal analysis. So this model is a metal part, an iron part. Imagine it's very hot at 1000 Celsius degrees, and you have to blow some air on it in order to make it cool down. So the aim of the analysis is finding out how much time it will take it to cool down. How do you set up an analysis like that? Well, first of all, in general settings, You need to activate heat conduction in solid in order to allow interaction between the fluid and the solid. Then you absolutely need to activate radiation, because when there are high temperatures, is the most important heat transfer mode. The analysis will be time dependent, and you have to, of course, activate gravity to better calculate convection. Then, for what concerns fluid, I will choose air. I will choose the solid material of the part, which is iron. In the world conditions, you have to define the emissivity of the iron surfaces. In the engineering library, there's already iron as a material for what concerns emissivity, so you don't have to figure out the value. It's already in the library. And finally, in the initial conditions, you define first the temperature of a solid, which is 1000 Celsius. Then you define the temperature of air, in this case it's 30 degrees, and also the velocity of air that is blowing on this part. In this case, the air is blowing in the Y direction, so from below, following the direction of the blue arrow you see on the 3D model. Okay. Said that, you don't need to add anything else than maybe some goals. I put some goals to monitor the temperature of solid, and also you could add some goals to monitor velocity. I'll show you quickly the results. This is the result of the temperature of air, and you can also add a surface plot showing the temperature of your 3D part. I would suggest you to put the scale in a way that will emphasize the temperature change in the solid when you're creating the animation. So I would put in the solid 1000 degrees as maximum, and 356, which is the lowest temperature that the solid will reach at the end of analysis. And the same for the fluid, you would put some temperatures. So I already have the animation. Maybe I will turn the model around so that you can see it better. I will play it. Basically, you follow the same actions that Alessandro showed. You create a scenario, and then you basically add both the cut plot and the surface plot, and as the animation plays, you will see the solid turning from red to blue, and also you will see that the air near the solid will become hot, and the convection will have it go towards the roof of the building where this model is supposed to be. Okay, let's move on. Another tool you can use is the Transient Explorer. If you want to create a transient animation, of course, you have to calculate full results for each time step, and this consumes a lot of disk space and also takes time. If you use the Transient Explorer, you can simply calculate the results that you are interested in. So we'll just save time in calculating, also time in saving this. It will save also some disk space. So basically, what you do with Transient Explorer, you can move a slider, and it will show you how the results are changing at each time step, and you can apply it to cut plots, surface plot, and also to XY plots. So how does it work? Basically, you have to go to calculation control options, and you have to go to saving, and you have to activate Transient Explorer mode. You have to define at how many time steps at which time step you want to save your results, and also define which parameter you want to save. Then you launch the Transient Explorer, and when launching it, you will be able to move the slider, and you will see in this case the von Karman vortex that is developing, and also will show you the velocity in the XY plot. I will maybe show you again the Transient Explorer. So basically, what you have to do, you have to define it, at which iteration you want to save, and also here the parameter that you want to save with the Transient Explorer. Okay, so next is the SOLIDWORKS Flow Simulation ideas, how we manage them, and how you can submit them. So basically, the software is growing, and each year we'll receive more than 6,000 enhancement requests. It's very difficult to guess which are the most important to you. So usually at the end of the year, in late October or start of November, we give you the ability to submit your ideas on a portal that is called Top 10 List. So basically, there is a first phase in which you can create ideas and propose as many as you want. And then there is a second phase, usually in January, when you can vote the ideas. And you can see here the interface. You can see how many people viewed your ideas. People can also comment your ideas to suggest improvements. And also you can see the number of votes on the idea. The top 10 ideas are presented at SOLIDWORKS World. It's either on stage or lately we are presented it in a dedicated session with our R&D manager and also with our CEO Gianpaolo Bassi, so that customers can discuss more in detail those ideas and maybe be involved in some product R&D project. So with here are some data. Since 2001, 70% of these top 10 ideas have been implemented. So this means that SOLIDWORKS is driven by you, by the customers. We listen to you. Also, don't be discouraged if your ideas don't make it in the top 10, because we really care about each idea. It's very important for us to get some inspiration for future development. We want to put some features that are really important to you. Also, we understand that maybe you could submit your ideas, but maybe you don't have much time. So we invite you to ask your reseller to do it on your behalf. So you propose the idea to the reseller, and the reseller will submit the idea on the portal, and obviously will give credit to you. Okay, let me launch a poll just to get some feedback and understand if we could capture some interesting features for you. Okay, I'll wait a couple more seconds. Okay, thank you for this feedback. I'll share with you the results. Thank you very much. I will keep on showing you many interesting product features in this Your Personal Trainer series.
Yeah, thank you very much.
Let me launch a last poll. Okay, since it's 3 p.m., I'll close the poll and share it with you. Okay, thank you. This is amazing, amazing feedback. Okay. Then I'll summarize the next episode. So in early November, we will show you a presentation that we showed it at SOLIDWORKS World 2015 called Your R&D in SOLIDWORKS. We'll show you all the features that can automate product optimization with both SOLIDWORKS Simulation and SOLIDWORKS Flow Simulation, and some case studies by customers that are actually using those optimization features, some real cases. At the end of November, we will show you the design to manufacturing workflow, so smart manufacturing from concept to production. And finally, in December, we will show you mechatronic design, how you can integrate mechanical design, electrical design, and PCB design. Next, there is a very interesting idea that I love by Alessandro, a proposal for the next year Your Personal Trainer series. So I'll let Alessandro comment on it.
Yes, the idea basically is very simple, is to give you something and to take something. So we would like to refrain, let's say, the Your Personal Trainer series towards more on your simulation problems, let's say issues, so also on your models. So we like to have your simulation, and you can get advice from us to improve productivity, to improve results, or to assess some issues if you want. Of course, we are not, let's say, the technical support, but here the most interesting cases we will show on this kind of webinar series. Of course, there are some caveats. Basically, we are addressing only current simulation portfolio customers, so under subscription. It's not meant to be a consulting activity. We are like to give you advice, just advice, not consulting, engineering consulting activity. Of course, there will be a selection process, and if you want to us to show your models, of course, you will assign a waiver. That's not normal. Also, we would like to have you as a guest, if you want, on our webinars to present your case and to see with us, let's say, how to address better your model. So you can write to us, and in the next slide we will see our emails. It's gone.
Yes.
So here you can have our emails. You can send us ideas, just ideas for 2019 for this series. You can send us models, proposals, and we will be very happy to address all of the requests. So in this case, also I don't see any questions at all. I have to thank you very much for your attention and for the feedback since now, and thank you, of course, Alessandro, for this webinar together. And we will await you for the next webinar, for the next episode of Your Personal Trainer series. Okay? So good evening, everyone. Goodbye.
Thank you. Good evening. See you in November.
Bye-bye.